Hello guys, today we will discuss about vectors. Linear algebra concerned with two types of mathematical objects. One is matrix and the other one is vectors. We already discussed basics of matrices in our previous video. You can go through it and you can take some basic information about matrices. Now here today we will discuss some basic things about vectors. That means what are vectors and what is the operations on vectors. That means the addition, subtraction, or in fact the scalar multiplication of vectors we will discuss here. Also, we will discuss about the length of a vector, which is also called as the norm. And finally, we will finish this lecture with the concept between the distance between two vectors. That means we will see some basic things about the vectors. The vectors and matrices are closely related, and the much of linear algebra is concerned with that relationship. That means the vectors and the matrices, they are very closely related. So we will see that what is that kind of relationship here. So let us begin with the vector. So what is a vector? Vector is a physical quantity which has a direction and the magnitude. So that vector, if suppose you have this vector, so if you see that this tail, it is called as the initial point, and this arrow side, this is called as the terminal point of the vector. So for example, if this is point A, this is point B. So we will say that this V is a vector AB. And suppose this point B has coordinates as x2, y2 if we are working in R2, and point A has coordinate as x1, y1. So we will say that the vector component of V x2 minus x1 and y2 minus y1. So these are called as the vector components of the vector V. So that means if we have initial and terminal point is given, so we can find the vector component of that vector. Suppose we take any point, and suppose this point has a coordinate as x1, y1. So you know that this is your x-axis, this is y-axis, and in general we say that this whole space, this we call it as it is our R2. Any point in the plane here, we call it as a vector. We can, why? Because we can take that point as the terminal point, and this origin point, this point, we can take it as the initial point. Now join this. If you find the vector component for this vector, so you will get x1 minus 0, y1 minus 0. That means ultimately you will get the vector components as x1, y1. So we will say that these points are vectors. Similarly for R3, that means if suppose this is x-axis, y-axis, and z-axis, this is origin. Take any point. So you know that any component, it will have coordinates as x1, y1, z1. So you can take that point as the terminal point, origin point as the initial point, and this vector component will have x1, y1, z1 as their components. So this is our R3. So vectors in R2 will be of the type, vectors in R3 will have three components. It is in R3 in general. If we have n components, that means that vector is coming from Rn. So if you see that any if you see, for example, R3, these are the representation of three components of vectors. So we can denote it also as, that means any representation which preserves the order of the appearing components, it will be a vector. If you see that this is your row vector, or if you write down that vector in the form as a matrix x1 y1 z1, so this is your column matrix. So same vector x1 y1 z1 can be written as the row vector, row matrix, or column matrix. We will use either this form or this form or this form according to the need of the question. So first operation is vector addition or subtraction. That means suppose if you have two vectors u, v, in, for example, if you take in R3, that means you can say this is, because it is in R3, so it will have three components, u1, u2, u3. U plus v, it will be component wise addition. So first component you will add to first component of the second vector, so you will get u plus v. Similarly, second component with second component, write it here, and third component addition with third component, write it here. So in this way addition is defined. If you have to write down subtraction, so in place of this plus sign, write down minus. You will have u1 minus v1, u2 minus v2, u3 minus v3. So in this way you can define the addition of two vectors, and if you notice that it is the addition, it is again in R3 because it have three components. Second operation is the scalar multiplication. Suppose you have any vector v and you have any scalar k, because v it is in Rn, that means it will have n components, so it will be multiplied by e. So if you see that basically what is your scalar multiplication, suppose you have this vector v, if you find 2v, so you will have same vector but its magnitude will be doubled, because this is you are multiplying by 2. If you multiply with half v, so it will be a same vector but half of this length. This is minus v. You have the same vector, same magnitude, but the direction is opposite. Now let us discuss about equal vectors. Suppose you have two vectors, then we say that these two vectors are equal vectors if, because it is in Rn, so we can express it as n tuples. So we will say that these two vectors are equivalent vectors or equal vectors if and only if their corresponding components are equal. That means u1 is same as v1, u2 is same as v2, un is same as vn. So first component of u must be equal to the first component of v. So this is the definition of equal vectors. Now let us discuss about the linear combination of vectors. Suppose you have a vector w, it is in Rn, then we say that this w is a linear combination of the vectors. So if you can write down W as the linear combination of these vectors. Linear combination means you just multiply each vector by a scalar. So if we can find out these scalars C1, C2, Cr such that their linear combination comes out to be as W, then we say that this W is a linear combination of the vectors V1, V2, Vr, where these Ci's, where I running from 1 to R. So these Ci's are called as the coefficients of the linear combination. So that means if you can find out these Ci's such that when you multiply the vectors, these V1, V2, Vr, and this sum is same as the vector W, so then we say that this W is the linear combination of the vectors V1, V2, and Vr. So let me give you an example of a linear combination. So we have to check that W is a linear combination of U and V or not. So we will say that suppose W is a linear combination of U and V. It means you can find out some scalars C1 and C2 which can be written as the linear combination of the vectors U and V. That means if we can find out the values of C1 and C2, then we can say that this W is the linear combination of U and V. And if we are unable to find the values of C1 and C2, satisfying this equation, then we will say that W is not a linear combination of U and V. So just write down the values of the vectors. W is, now just do the multiplication and add them. 4C1 plus 2C3. Second component minus C1 plus 3C2. We just study about the equal vectors. So two vectors are equal only when their corresponding components are same. That means first component equal to first component, second component equals to this second component. So we have, so simplify these two equations. You will get the value of C1 as 2 and C2 as 1. So if you see that we find the values of C1 and C2, that means this W is the linear combination of U and V. And if from this system of linear equation we are unable to find any values of C1 and C2, that means this system of linear equation has no solution, then we will say that this W is not a linear combination of U and V. But here we find the values of C1 and C2. That means this W is the linear combination of U and V. Now we will discuss about the norm of a vector. So norm is what? Norm means length of a vector. So if suppose we have any vector V in R2, that means having two components V1 and V2, it is in R2, then the norm of the vector V, this is the notation for norm, length of the vector V. So how the norm is defined? So it is defined as, just take the square root of the component squares addition. So this is the length or the formula for finding the length of a vector in R2. If you have a vector in R3, so its norm, what you do? Just component square, U1 square, U2 square, U3 square, their addition, and just take the square root. So it will gives you the norm of the vector. So in general, you can generalize this. Suppose if you have a vector, you can generalize this norm of a vector. If suppose you have a vector u having n components, general case u1, u2, un. So norm of u is nothing but the square root of the sum of the components square. So u1 square, u2 square, un square, take its square root. So this is called as the norm of a vector. We will say that a vector u is a unit vector if its norm is 1. Okay, so if length is 1, so that vector is called as a unit vector. Now let us discuss some standard unit vectors. Suppose it is your R2. You have this vector. So we denote this vector by I, j as 0. And if you find out its norm of I, it will be under root 1 square plus 0 square by definition. Similarly, if you find out the value of norm of j, it will be 1. So this I and j are the standard unit vectors of. Similarly, if we talk about in R3, so this point have the coordinates as 0, 0, 1. So we denoted by as I, j, and k. And if you find out the norm of I, similarly you can find out the values of norm of j, it will be 1, and norm of k, it is 1. So we will say that this I, j, and k are standard unit vectors in R3. In general, E1, E2, that means the one at this number place, and so on, En. Each element has n components, and 1 is the place where this EI is stand. That means you will have in EI, you will have 1 at the ith place. So this E1, E2, En are the standard unit vectors for Rn. So if you notice one thing, suppose you have any vector, so you can write down this vector as the linear combination of the standard unit vectors. Do the multiplication, add them, you will get the same left hand side. So this is, so either if this number is written, this expression is written, or this is written, they have the same meaning. They are the vectors in R3. Similarly, if you have any vector in R2, so you can write down this vector as, suppose you have any vector in R4, so it can be written as, where E1, E2, E3, E4 are the standard unit vectors for R4. So I hope that these expressions are clear to you. Now let us discuss the normalization process. Suppose we have a vector u. If you find out its norm, its components square, so its norm is root 29. But if suppose we have to find a unit vector in the direction of u, so how we will find that vector? So that process is called as the normalization of this vector. So we have to find a unit vector in the direction of u. So how to do it? It is given by this formula. So if you multiply the vector by the scalar 1 upon norm of u, then you will get a unit vector in the direction of u. So you can do it. Norm of u is root 29. U is 2, 3, and 4. It means, so this vector v is a unit vector, and I leave it as an exercise for you. You can check it that the norm of v comes out to be 1. So this process is called as a normalization of a vector. So if you see that we find a vector v in the direction of u, and if you have to find out a unit vector opposite to the direction of u, so just do find out this vector and do multiplication with minus sign. So this will be a unit vector to the opposite direction of u. So we will conclude this lecture with the distance between two vectors. Suppose you have two vectors p1 and p2, and we have to find out the distance between these two vectors. Suppose p1 has vector component as x1, y1, z1, and p2 has vector component as x2, y2, z2. So distance means what? We are finding the length of this vector. So if you have to find out the length of a vector, so you have to find first the vector component, and the vector component is given by the formula x2 minus x1, y2 minus y1, z2 minus z1. So basically, in finding the distance between p1 and p2, we have to find the length of this vector. Two components are given. You can take anyone as tail and anyone as the initial point or head. Okay. So just find the vector component and now find its norm. So if you find its norm, or the distance between the vectors p1 and p2, it is same as the norm of the vector p1, p2. And if you have to find out the norm, so component square. So first component is x2 minus x1, y2 minus y1, and z2 minus z1. So this is the formula for finding out the distance between two vectors. So two vectors, in general, two vectors are given p1 and p2. Suppose the coordinates, or I should say that the vector components for the vectors p1 and p2 are x1, y1, z1, x2, y2, z2. We have to find the distance between these two vectors. So if we treat it as a vector, so we have to find out its length. Length means we have to find out its norm. And how to find out norm? Just component square. So we got this one. And you can generalize even. If suppose you have two vectors uv in Rn, means if you have u having n components, u1, u2, un, we will have components as v1, v2, vn. Then distance between the vectors u and v is what basically the norm of u minus v. It is what? Under root u1 minus v1 square, u2 minus v2 square, and un minus vn square. Either you find out norm of u minus v or v minus u, it will comes out to be same. For example, suppose you have two vectors u. You have to find out the distance between u and v. It is what? Norm of u minus v. So norm of u minus v means u1 minus v1 square, u2 minus v2 square. Simplify it, you will get 1 square so the distance between the vectors u and v is 3 unit. So these are some basic operations in vectors. So we discussed the vector addition, the scalar multiplication, and what is the norm, what is a unit vector, what are the standard unit vectors, and how to find the distance between two vectors. These are some very basic concepts in vectors which we have discussed in detail here. Now in our next lecture we will discuss about the dot product and the cross product of two vectors and the angle between. That means some more concepts related with vectors, which we will discuss those things in our next lecture. If you enjoyed this video, so please guys share it with your friends. Thank you so much.